right, we are now recording. Here we go. And let's get up. Let's see, sorry about that. I should have opened PowerPoint ahead of time. Now, the last time I did it from here, it insisted on having, no, okay, sorry, blank presentation. Okay.
I thought you were going to use that, the one that we...
Yeah, I said I don't think we have need for, graph paper in this course. All right, okay. Okay. All right, now go back through this again. Sorry, I should have had this done. Now, I think we're on the same page. All right.
Same slide.
Shifting gear. Same white screen. Okay. Or white page. One or the other. Okay. This is elementary linear algebra. And we're starting at the top of page 6, solving a system of linear equations. Now, I'm not going to solve these. You should be able to do that from what you've done before. What I want to start with is some definitions. All right? So I guess I am going to write these. And this was where I was wondering if line paper might not be easier, but it doesn't really matter. Here's okay. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to negative 4. And 2x minus 5y plus 5z is equal to 17. Okay. That's a system of linear equations, 3 equations, 3 unknowns. We think it should be solved. Here's another system of linear equations. First equation looks exactly the same. X minus 2y plus 3z is equal to 9. Okay? Second equation doesn't look quite the same. It's y plus 3z is equal to 5. Okay? The third equation doesn't look at all like the third equation either, but it's z is equal to 2. That is an equation. Which of those two systems of equation would be easier to solve? Why?
Because all you got to do is plug in the bottom one into the middle one, then the answer for y and z, and the top one.
Okay, that has a name. It's called back substitution. Okay, we'll be using that concept. Now, this system here on the right is called, here's a name for it. Never used this in algebra before. This is called row echelon form. Row echelon form. Now, I'm not totally sure what echelon stands for, except that it kind of seems like the same kind of word that escalator would stand for, would come from. So it's a stair step. Okay? It kind of has that appearance. It means it has that stair step pattern with, and the key is here, another key, yeah. Here, the variables, the leading coefficients are a variety of things. Here, the leading coefficient, 1, 1, echelon form as well. It has to be stair-step, but it also has to have the leading coefficient of each step, okay, is 1. Okay? The others can be whatever, but the leading would be 1. What's that?
The 0. I said I can't help but see this in matrix form.
That's exactly what you should be seeing. That's the only reason I'm mentioning it, because we're going to use the same term later. Okay? Now, and again, 1.1, I'm just hitting the parts that we're going to use in matrices. Okay? Jumping over to page 7. Operations that produce equivalent systems. Okay. Now, here's something else. They didn't tell you this, but I'm going to tell you this. These two are the equivalent systems of equations. It's not that I just made them up. I copied them out of the book, but they didn't just make them up. And here's why. Notice what happens if you add these two equations together. That gives you 0. This gives you y. That gives you 3. That gives you 5. 5. Okay? Now, it's a little harder to see, but I don't think impossible to see, is that, let's see, multiply the top equation. Well, we won't get it. I thought it was going to be easier than that. It's not, so don't sweat it. Those are equivalent. Okay? Now, what do we mean? Okay, so, okay. Bottom of page 6. Two systems of linear equations are equivalent. Okay? Now, the word equivalent, what does that word mean? Equivalent. I messed up my E there. Okay. Not quite. Those are not the same. But equal value. Okay, equivalent, fine, but equal values. Okay? Z equal 2, Y equal, what, -1?
Right.
Okay? And X equal, or whatever it turns out to be. That satisfies that system. I can almost guarantee you those same thing would be exactly this too. Second?
I think X would be -9.
It might be. I just didn't plug it in.
-6 times 2 is 12 plus 6 is 18 minus -15 plus 9.
Okay, so let's say -9. Okay? Let's see. -9, we said -1, right?
Yeah, so that's
Plus 2 would be -7.
I thought it was -3.
Huh?
I thought you said -3.
Where Y?
Oh, it's -1, so yeah, I said it.
Okay. Yeah. I wasn't following what you did, but okay. But whatever. The same solution will work for both. They have equal values, so we call those equivalent systems of equations if they have the same solution, equal values. So, what are operations that produce equivalent systems? Each of the following operations on a system of linear equation produces an equivalent system. Here are those three. Number 1, interchange any two equations.
Switch the rows.
Yes, switch the rows. Any two equations. Okay? So, yeah, of course, if you swap the first and the second, that would be equivalent. First and the third, second and third, whatever, just swap any two, you're going to have an equivalent system. Kind of a no-brainer, right? Okay, that's one. Second operation you can do that gives you an equivalent system is multiply any equation by a non-zero constant. Okay? Yuck! Okay.
You might be able to do that with the arrow keys.
Huh? With the arrow?
Yeah. go to that page, you can just hit this.
Oh, I
page.
see. Okay, thanks. Okay. All right. Now, none of these have a constant multiple, but we could take this equation, multiply it by -1. And that would be x minus 3y is equal to 4. That's an equivalent thing. You multiply the entire equation, not just one side or the other, entire equation by a non-zero number. Okay? Now, those two are pretty simple, and now this one maybe takes a little more faith to believe. Add a multiple of one equation to another equation, and you're going to have an equivalent system. Okay? Now, we really did this too. We added these two equations together. We added 1 times this to that, and we got an equivalent equation. Okay? So we did it with just adding, but you could add a multiple to it, and it works too. In fact, if you remember solving systems of equations, we called that method,
It wasn't substitution.
no, it was elimination by addition. And that's exactly what we used. Remember? Yeah, okay. So, that's the third. So you can do those three anytime. Okay? Now, don't go around multiplying anything by 0. And don't go around dividing anything by 0. Because remember, multiplying by any constant not equal to 0 is actually the same as dividing by a constant not equal to 0 too. Like multiplying by 2 is dividing by 1/2, isn't it? Or multiplying by 1/2 is the same as dividing by 2. So you can either multiply or divide any equation by a constant as long as that constant's not 0. Okay. Can't divide by 0 because that's never allowed. You don't want to multiply by 0 because you lose all meaning of your equation if you do that. Okay, now rewriting a system of linear equations into row echelon form usually involves a chain of equivalent systems, each of which is obtained by using one of those three basic operations. That process is sometimes called getting it in row echelon form or Gaussian elimination. Okay. Carl Friedrich Gauss, German mathematician, recognized with Newton and Archimedes as one of the three greatest mathematicians in history. Pretty high up there, okay? He used a form of what is now as Gaussian elimination in his research. Although the method was named in his honor, the Chinese used an almost identical method some 2,000 years prior to Gauss. So, as clever as we think we are, so many things we find out the Chinese were doing way before us. We just don't know beans about their civilization. Okay, it didn't filter down. These were done independently. I don't think Marco Polo could have brought that much back with him, and he may have even been after Gauss. I don't know. So anyway.
I started reading about Gauss because I'm going to do a paper on him.
I was just going to say, it'd be a great paper topic. Okay? And we named this after him. So, keep that in mind. Now, there are times when you come up with do Gaussian elimination, you get it into this kind of form here, you do your back substitution, and you wind up x equals something, y is equal -1, z is equal 2, or something like that. Okay? That then is a solution. Now that's a unique solution. Okay? We say two things about the system. Number one, the system is consistent. It has a solution. We talked about this before. The second thing we say, these three equations are independent of each other because it produces a unique solution. Okay? So, huh?
So they are a part of the system.
Yeah, exactly. Now, just keep that in mind. And if you were to plot each of those equations. Now that would be in 3 space. One would be a plane this way, one would be a plane that way, one would be a plane that way. The only place they intersect would be 1 point. Okay?
And that's the coordinates of that point?
And those are the coordinates of that point. Exactly.
Very well answered.
Yeah. And z equal 2 would be a coordinate of that point. X, y is equal -1 would be a coordinate, whatever x is that. Now, if you did that one and did z is equal to 2, y is equal to -1, and then x equal whatever it turns out being, those 3 planes connect at that same point. They just be 3 different planes, but they come to the same point. So you see an equivalent system of equations will have different planes, but they'll all intersect at that same point. Okay, that's what we mean by equivalent. All right. Now, consistent means it has at least one solution. Okay. If we had a system of equations that this plane did this way, and this plane did that side, okay? But then your third plane was down here, exactly parallel to this plane, you're not going to get any solution to that. You won't have anything that satisfies all 3 at the same time. That's going to be an inconsistent system, okay? So keep that in mind. Now, you could also have a plane here, a plane there, and then another plane here, and okay, that would be inconsistent, the one I just described, but what I meant was plane here, a plane there, and a plane there. They would have a line that all the points on that line, which is an infinite number of points, would be solutions. That is a consistent system, but now they would not be independent of each other. That would be the equations in that would be dependent. 2 or more of one adds to the same as the other. Okay, so it would be like in 2 space, there's a consistency with one, okay, and independent. That's consistent but dependent. That's inconsistent. Okay.
Let me ask you something else. If they were all equal to 0, would that be trivial?
That's in the other course. No, yeah. You mean,
Like all
yeah, if that 9, -4, and 17 were all zeros. Okay, now we call that a homogeneous system. Okay, that homogeneous system, certainly the trivial solution would work on that, because x equals 0, y equals 0, z equals 0 is going to produce zeros there. Absolutely. Now, if there is some other solution other than that trivial solution, then that system will be consistent, but it'll be dependent. Okay? I think that's always going to be the case. If that's the only solution you have to that, then we're going to get to this later. Then you could plug in any other numbers there, and you could come up with, consistent, consistent, exact solutions. I mean, unique solutions for whatever. So hang on to that thought. That is a key thing. If all those constants are 0, and the only solution, certainly the trivial solution would be a solution, but if that's the only one that is, then you have a consistent system, and they are unique. I mean, yes, they're independent. Yeah, they would be both of those, because obviously, if the trivial solution is a solution, if you had any other solutions, it's not unique, so it's going to be dependent. Okay, so that would be if the trivial was your only. Okay, now. What's that?
So that's the other course.
Yeah, yeah. All right. Now, I don't know. Yeah, you both had trig under me. And this Ron Larson, remember I said I liked him better than, say again? Didn't like the publisher, but I liked the author. But he does some things in this book that sort of baffle me a little bit, but every linear algebra book seems like they do the same thing. They will sometimes introduce not just a trivial concept, an important concept in their exercises. Why didn't they put it in the text, you know?
Like
a whole definition. Yeah, right. Exactly. I don't see any in this set, so we're not going to go there, but occasionally he'll do this. Another thing that he does here that sort of stokes me a little bit is that if you remember the trig class, when he wrote a vector, he put them in angle brackets. Remember? If you have parentheses there, that was an ordered pair, ordered triplet, ordered whatever. That was a point in space. But if it was in angle bracket, that was a vector in space. In this book, everything's in parentheses. So why did he change? So you just have to know by context whether you're talking about a point or a vector. Okay? Kind of bugs me, as you'll tell. Okay? So those two things. But one of the things he does very positively here is, see calctrack.com, www.calctrack.com for worked out solutions to the odd number exercises. That's the thing I find so powerful that he does. I haven't found any other author, I'm not saying there aren't some, but that do this. Now,
What condition is that?
7th. But I bet you he did it in the 6th and the 5th. He's been doing this a long time, I think, to get the 7th editions office. Okay. Now, the one thing he did in the pre-calculus book is once he did an example, then he would do what they called a quick check, or you had some sort of name for it, and it was another example or two that you do on your own, and then you could go to larsonprecalculus.com and see those answers. He doesn't do that in this one, okay? And they don't have PowerPoint in this one. So there are a few things with the calccheck.com he still does, which I think is great for students. And to me, it almost makes WebAssign, why bother purchasing that? Anyway, now 1.2. We are going to introduce matrix, okay? And I think you'll see why I did what I did in 1.1, just hitting a few things. Those terms that we hit then, they apply to matrices as well. What is a matrix? Section 1.1 introduced Gaussian elimination as a procedure for solving a system of linear equations. In this section, we will study same procedure, and it's still called Gaussian elimination, more thoroughly, beginning with some definitions. The first is that of a matrix. So let's do okay. Definition of a matrix. M in positive integers. M and N are positive integers. Okay? Now, an M by N, okay, that's, you write it with the, like the time sign, but you say M by N. It's not a multiplication. Yeah, kind of like that. Yeah, like you're saying this room is 4 feet by 10 feet, you know, or something like that. Okay, it's way more than 4 feet, but you get the idea. Yeah, and you use that same type term there. An M by N matrix is a rectangular array okay? And here's how you write it. A11, A12, A13, dot, 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 A1N. Okay? A21, A22, A23, A2N. A31, A32, A33, A3N. What would become at the bottom? M1, A M2, A M3, A M N. A rectangular array of numbers with M rows, N columns. Okay? And typically we refer to the elements or members of that matrix with a double subscript. The first subscript indicates the row that it's in. The second one indicates the column that it's in. So there will be M rows, N columns. Make sense? That's how we define a matrix. Now, in which each entry, Aij, okay, of the matrix is a number, okay, and M by N matrix has M rows, N columns. I've already said that. Now, matrices are usually named by capital letters, and typically if you name the elements little a's, you would typically name the matrix capital A. Okay? It's just sort of a convention. There could be exceptions to this and whatever, but that's usually the case.
What is that insert?
Each. Yeah. Okay. Each entry, Aij. And this is actually, if you were doing this, you really should throw in the thing I going from 1 to N and J, 1 to M, and J going from 1 to, I guess these should be equal to N. The first representing the row number, second representing the column number. Okay? Any entry, pick an I or J. They're all integers. Okay. The entry Ij is located in the ith row, J column. The index, little I, is called the row subscript because it identifies which row the entry lives. And the J subscript is called the column subscript because it identifies the column in which the entry lives, stays, lies, whatever. Okay. Matrix with M rows and N columns is said to be of size M by N. We're kind of saying it backwards now. When M is equal to N, what do we call that? No, not necessarily. This one is a rectangular matrix. A square matrix, exactly. So that would be a square matrix. Okay? And we'd say it's a square matrix of order N. You can't call a rectangular matrix of some order because typically the M and N's are not the same. But if it's a square matrix where M is equal to N, then you call it a square matrix of order N. They use N rather than M. Interesting, but they don't. Okay. Now, when you have that square matrix, and let's say these M's and N's are the same, so N, okay, then what's this one called? Your main diagonal. This is also a diagonal, but we never use it, so we don't even refer to it. So most of the time we'll call it our diagonal, but really it's our main diagonal.
The one we want to be certain things.
The what?
The one we want to.
Yeah, where IJs are equal. Yeah. So AII or AJJ or whatever. that would be your main diagonal entries. Okay? So, we talk about size, but the size is the what we call it, the thing that we call it. So let's just do so. Okay. Can you give me a matrix whose size is 1 by 1? Give me one. 1. Doesn't have to be 1. It could have been 3.7. Okay? It could be anything. Just a single number. Not a very interesting matrix. Why make it a matrix? But it's that. 1 row, 1 column, 1 entry. One and only one entry. And it could be any number in the world. Now, certainly, rows and columns are integers, but the entries don't have to be integers. They could be anything. Irrational. You could even go to complex, but we're not going to. Okay? But it could be. So, here's I want you to give me a matrix that has size 2 by 2. Make up one.
1, 2, extra 3.
That's certainly a 2 by 2 matrix. Okay? I'll give you another one. Oops.
Very interesting.
Not very interesting. That's a 0 matrix, but it's a 0 2 by 2 matrix. 1 by 1 0 matrix would be just the number 0. Now, they don't have to be square. You could have a 0 matrix that was 2 by 3. 0, 0, 0, 0, 0, 0. Okay? But a 0 matrix is a matrix at all. But the one you gave me is a perfectly good 2 by 2 matrix. How about a 2 by 3 matrix?
1, 2, 3, 4, 5.
Okay?
I'm very creative.
Okay. That certainly is 1, but remember the entries don't have to be integers. They could be any number. So even something that looks as bizarre as this and I want to do, that's not the one that's in the book, but I want to throw that in too.
Just so you know it's all kosher.
Yes, they don't have to be, this is an irrational number, that's an irrational number, that's an irrational number. That's a positive number, negative number, positive. You can positive too, by the way. But you could have fractions, you could have decimals, you could have irrational, rational, it doesn't matter. Okay? Those are all legitimate 2 by 3 matrices. Yeah. Yeah, no, I'm not going to. Okay. Now, one common use of matrices is to represent systems of linear equations. Okay? And y'all keep me track on time too. Okay? Now, how you get from a system of linear equations to a matrix, we write down the numbers that are the coefficients. Forget about the variables. Okay, don't forget totally. But I guess I need to take that back. Time out before we go further.
Make sure.
Very good. Make sure your x's are under x's, your y's are under y's, and make sure your equal signs are under equal signs. Make sure they're in exactly the right order. Then you pull the coefficients out. Okay? If you're missing a y, leave a space there. That coefficient's going to be 0.
I was going to say, yeah, it's going to be 0.
Yeah. So, make sure that's the case.
It would still be okay just to,
What's that?
Equations, like write in plus 0 or whatever. Right?
Yeah, that would be perfectly legitimate. We usually don't do it, but it would be. Okay? So let's start with the system. Oh, there it goes. All right? Here's a system of equation. X minus 4y plus 3z is equal to 5. Okay? Minus x plus 3y minus z is equal to negative 3. 2x minus 4z is equal to 6. Okay? Now, we talked about the coefficients. Those would be the x minus 4, 3, minus 1, 3, minus 1, 2, 0, negative 4. But then you also have the solutions over there. Okay, what we do, we augment the matrix from the coefficients with those solutions. So that's why it's very important you make sure your variables line up and your equal signs line up. And then you can augment the matrix by just taking out the variables and the equal signs once they're lined up. So this would be represented by this, and we call it an augmented matrix. And by the way, the square brackets around arrays of numbers, that indicates it's a matrix. So what would this be? 1, negative 4, 3, 5. Negative 1, 3, negative 1, negative 3. 2, 0, negative 4, 6. There's your augmented matrix. Now, sometimes in the past, I found it convenient to do a little dotted line in between the coefficient matrix and the, what I call the solution vector. Getting into something else. This book doesn't, so I've gotten away from doing that. But there's always a part of me that sometimes I'll go and put a dotted line in before I think about it. If I do, there's nothing wrong with that. It just indicates. So, yeah. Okay. The only problem that comes with it when I put those dotted lines, sometimes the one dash will wind up just next to the 5 and it'll look like a 15. So for that reason, I tend to.
May miss the negative sign or something like that.
Yeah, it could do that too. So there are other times I tend not to. All right. So this part of it here is called the coefficient matrix. They don't give a name for the other, but the entire thing is called the augmented matrix. It has the coefficient matrix with the, what I call the solution vector, though they haven't defined those terms yet. Okay? Now, I mentioned elementary operations you could do on equations. Guess what? Now we call them row operations, because each row of the matrix represents an equation. So we call these elementary row operations. And guess what they are? Exchange any two rows. Number 2, multiply any row by a number not equal to 0, a non-zero number. And 3, add a multiple of a row, of one row to another. Okay, basically exactly like we said before, except everywhere before we said equation, now we're saying rows. Same thing. Okay? So yeah, same rules. Those are our elementary row operations. Okay? When you do that, any one or more of those that you do, then you come up with an equivalent matrix. Just like an equivalent system of equations, an equivalent matrix. Okay? And we said they are row equivalent when one is obtained from the other by a finite sequence of these elementary row operations. So again, exchange two rows, multiply a row by a non-zero constant, add a multiple of a row to another row. Now for some reason, I'm sorry. I was wasn't reading carefully. On this page 14, they repeated that with equations in it, and then wrote it with rows. So I only wrote it with the word rows in there rather than equations. Okay, although elementary row operations are simple to perform, they involve a lot of arithmetic. Guess what? No algebra, really. No. Yeah, that and multiply and divide. That's all you're doing. Simple arithmetic. It's a whole lot of them. And they're really easy to make mistakes. So be very careful. Be pretty organized. And unfortunately, you got to be sort of neat too. Yeah, don't go there, okay. All right. So, now I'm going to combine a couple of things here. Okay? They're giving us a matrix. All right? 0, 1, 2, 3, 0, 1, 3, 4. Negative 1, 2, 0, 3. And 2, negative 3, 4, 1. All right. Now, I want to say this, I think I will, though there's part of me says I'm probably saying it too soon. What we're going to get to doing later is trying to, yes, all right, exactly. This can, the way it's written here, it cannot be written in row echelon form, okay, because you need that leading one, okay? So you never want that to be a leading zero unless all these are zeros, and then you can't help it. So first thing we would tend to do is flip, interchange the two rows. That's an elementary row operation. Pretty legitimate thing to do. So that becomes a equivalent system of matrix would be negative 1, 2, 0, 3. Don't just change that first two entries. You got to change the entire rows. 0, 1, 3, 4, 2, negative 3, 4, 1. Now, when I'm doing that, here's what I usually do. I usually write here what I'm doing. Row 1 interchanges with row 2. Okay? You don't have to, but I think you'll find maybe it'll help you eliminate. Interchanging two rows is not a big deal. But when you go back and look at this, it's easier to tell that's what you did. Okay? Now, okay. And that's exactly what my temptation was to be, though that's not what they're doing in the book. So what would be the next row operation you would do? Multiply the first row by negative 1. So here's what I would say here in my little side here. Minus row 1 becomes the new row 1. You just multiply it by minus 1. Okay, so that becomes 1, negative 2, negative 3. All right? And then the other two we just leave the same. 0, 1, 3, 4. And 2, negative 3, 4, 1. Right. All right. Now, okay, now a couple things have happened that were very nice. You've got a leading coefficient of 1. That was intentional. But then when we exchange these two rows here, we see we got a leading coefficient of 1, leading term, a leading 1 here in the second row, and that's starting to be row echelon. But you're absolutely right, we don't want a 2 there. What do we want there instead? A 0. Now, how do we get that to become a 0?
Multiply the first row by negative 2.
And add it to the third row. So, here's what I am going to say. -2 row 1 plus row 3 becomes the new row 3. There's my instructions. And I find it helpful to do those because if you especially have a lot of operations to do, it's helpful to be able to look and see what to do. So what happens, we're using row 1, so we're not going to change it, so it's 1, -2, 0, -3. We're not doing anything in row 2, that's like we wanted it, 0, 1, 3, 4. That's our new row 2. Now let's operate on that third row, and what do we get? Using that rule, 0, 1, 4, second, 7. Okay. Now, so you see we've exchanged 2 rows, we multiplied by a non-zero constant, and we've done the third one, added a multiple of one row to another row. Okay? Now, do you want to go on and wrap it up? Okay, you got a 1 here where you wanted it, 0's below it. You got a 1 here where you want it, and what do you want now? 0 below it. How do we get that 1 to become a 0?
Multiply the second row by -1.
You got it.
And then add it.
Negative row 2 plus row 3 becomes the new row 3. So we're not doing anything to row 1. We were happy with it, so we're just going to write it down. We're using row 2, so we're not going to do a thing with it either. We'll write it down. What's our new row 3? 0, 0, 1, 3. And guess what? We got our leading 1 there. So, wow, we have now got that matrix there into row echelon form. Okay, now, I wasn't supposed to take you that far with this first example, but it worked out so nicely. Why not? It showed every one of those elementary row operations, exchanging 2 rows, multiplied by a non-zero constant, and then twice we added a multiple of 1 to another. Okay? So, they give a couple more examples, but they're just, okay, I guess here's a good one to do too. Let me go to a clean page here. I'm not going to do all of them to that kind of detail, but I think this is important. Here's our original matrix. 2, -4, 6, -2, 1, 3, -3, 0, 5, -2, 1, 2. Okay. Now, let's just imagine we were trying to get it into row echelon form. What would be a good, okay. Cameron's stuck on exchanging 2 rows, and that would be a perfectly legitimate thing to do. But there's something else we could have done instead.
First 2 rows, or well, multiply row 2 by -1 and add it to row 1. That'd be kind of.
That would give you a 0 in row 1, which is not what you want. Okay.
Well,
all right.
it'd be -1
Look.
plus 2. And then.
Oh,
Yeah.
I see what you're doing. Minus row 2 plus row 1.
Right.
You could do that. You could. That's legal.
Not
But here's something else. Something you haven't thought of yet. Look at the first row carefully.
you can divide up 2.
Oh, divide the first row by 2, which is the same as multiplying by 1/2. As long as you're not dealing with 0, you can either multiply or divide. Either way. Okay? And that's what I wanted you to see. And none of these are any better than worse than the other, except this is a simplifying one. 1/2 of row 1 becomes the new row 1. Okay? You just make all your numbers smaller, and usually that's a pretty good thing to do. And that would give you what?
1, -2, 3, -1.
Okay, and then you write down the other rows. Now, if you haven't noticed it yet, I should have said something before I erased the previous screen. you're doing math, just simple arithmetic, okay? But you're also writing down a lot of the same things over and over and over again. Unfortunately, that comes with matrices. You just got to be careful. That's where, unfortunately, I know you don't like to say it, neatness matters, okay? Because you don't want to be interjecting.
But at least you don't have X's and Y's to write.
Exactly.
And
exactly.
equal signs.
And so therefore, take advantage of what you don't have to do and be a little neater with what you do. Okay.
Actually, I think I'm probably neater with matrices than anything.
Yes, I think you almost have to be. Okay.
There's more space, I guess.
Right. All right. Now, and the next one, basically, you've already done one, not the same way, but just about the same. So I'm not going to repeat that. Okay. Excuse me. Say again.
I think when I did matrices and I think calculus, either that or algebra 3 is probably my favorite part.
Right.
Class.
Yeah. It is. They are sort of fun. It's being careful. Okay.
You start getting into the really bad fractions.
Yes, that can get nasty. Okay. So we're going to do, and I'm just going to go back and take a look.
I don't think we have about 20 minutes.
We got 20 minutes? Okay, good. Example 3, I think I'll start with a clean page here. Okay. Example 3 here is basically the linear equations we had from one we looked at before. I hope you recognize it. X minus 2y plus 3z is equal to 9. Looking familiar? Negative x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17.
17.
It's a 17. My writing's bad, but my eyes were so itchy, I had to put down the pen in a hurry just to, so I could rub them. I don't know why. Goodness gracious. Okay. All right. Now, first thing we're going to do, guess what? Yeah, an augmented matrix. And what would that give you? 1, negative 2, 3, 9. Negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. All right. What's the first thing you want to happen? Okay, first, you want a 1 in the upper left. You got it. Okay. Yay, we don't have to do a thing. Second, we want to get rid of the negative 1. In other words, we want it to become a 0. So how do we make that happen? Row 1 plus row 2 is the new row 2. So since we're using row 1, we're going to leave it alone. 1, negative 2, 3, 9. Okay? What's our new row 2? 0, 1, 3, 5. Okay. Now, I'm lazy.
Yeah, I was just thinking that you could probably say that.
Okay. We got what we wanted there. Not going to write that third row again and then start over again. Let's just deal. What do we want to happen next?
Get a 0 with 2.
The 0 where the 2 is. How do we make that happen?
Negative 2 times row 1 plus row 2.
That's it. Negative 2 times row 1 plus row 3 is the new row 3. Okay? Now, when you are doing them like this, if you're using row 1 every time, write it and leave it and then, okay, deal with it. Okay, what does that give us? 0, negative 1, negative 1.
negative
Boy, you're stuck, aren't you? Yeah.
1.
Um,
Repeat.
I'm left-handed. I have to look over there. That's minus, yeah, negative 1,
All
right.
lines in my head.
Okay. Now, what do you want to happen next?
And so we got a 1 is the leading coefficient for the second row.
Okay, you wanted that? It's already done for you. So what next?
Get zeros below it.
A 0 below it. Okay. And how do we make that happen?
Add row 2 to row 3.
Row 2 plus row 3 is the new row 3. Now this time we're not doing a thing to row 1. It's already where we want it. 1, negative 2, 3, 9. And we're using row 2, so we leave it alone. 0, 1, 3, 5. And what's the third row become? 0, 0, 2, 4. Okay?
And then we can multiply by 1/2.
Oh, very good. Or divide by 2, but usually we say multiply by 1/2. You got a 1 here, 0's below, 1 there, 0 below. We want that to be a 1. Simplest thing to do, divide by 2. So row 3 divided by 2 is the new row 3. Okay? So this then becomes equivalent matrix 1, negative 2, 3, 9, 0, 1, 3, 5, and 0, 0, what? 1, 2. All right. Now we stop, pause, time out. This is where it's advantageous to have that dotted line in there. What this tells you is Z is equal to 2. Okay? That's right there. Okay? Z is equal to 2. Okay? The row above it says that Y plus 3Z is equal to 5. But Z is equal to 2, so that would be Y plus 3 times 2 is equal to 5. You don't have to take this many steps if you don't want to. That says Y plus 6 is equal to 5. That means Y is equal to negative 1. The top row tells you that X minus 2 times Y plus 3 times Z is equal to 9. Which tells you, when you plug those in, X plus 2 plus 6 is equal to 9. So that would be X equal 1. All right. So X equal 1, Y equal minus 1, Z equal 2. This is suggesting that's your solution, your one and only solution, and let's see if it works. Plugging a 1 in here, that's a plugging a 1 in for X equal 1, that becomes a 1. Minus 2 times minus 1 would be plus 2, right? So 1 plus 2 is 3, plus 3 times 2 is 6. 3 plus 6 is 9. Yay, that works. Have to work for the other two as well. Minus 1, minus 3, that would be minus 4. That's minus 4. Hey! How about the third one? 2 plus 5 plus 10. 2 plus 5 is 7, plus 10 is 17. Yes. Okay? So you see, these are equivalent equations, equivalent matrices, because they have the same solutions. Okay? And indeed they do. That, by the way, is called Gauss elimination of getting into row echelon form. You still call that your Gauss elimination form. All right, they got X equal 1, Y is equal to minus 1, and Z is equal to 2. Good for them. That last matrix, that right there, is in what they call row echelon form. Now, There is row echelon form. We just saw it. That's the stair step down with ones being the treads, right? Okay. Okay. Every leading coefficient is a 1. We're going to introduce another concept called reduced row echelon form. Okay? Before we do that, 10 minutes, I think that's going to be plenty of time to do. I'm not doing it exactly like the book does, but I'm going to take all this away. And I'm not going to say that this is the order I would have done it, but since we've gone this far, we can still go back and get it in reduced row echelon form. And what that means is for all these leading ones that we have, I always go to click on the sidebar and it's not there, of the taskbar. Okay? What we would have done earlier, but we can do it now, it's no problem, is for this leading one, we already got zeros below it. For this leading one, we got a 0 below it, but we also want a 0 above it. So how will we make that happen? 2 times row 2 plus row 1 becomes the new row 1. So let's do it. That would be a second. Oh, okay. Okay.
So that would be
1, 0, 9. That is a 0. Again, be neat. Okay. And then 19. All right. And the second row, we can't do anything. So copy it down. 0, 1, 3, 5. Third row is just like we want it. 0, 0, 1, 2. Okay. What's the next thing we want to happen? Let me clean that one up just a little bit.
Is it a 0 next to where the 3 is?
I like having this look neat, but I sure hate having to go through all these steps to do it. Okay. Yes, we want a 0 on both of the entries above the third one. So it doesn't matter which. Let's do with the 9. What do we do?
9 times, or negative 9
Negative 9 times row 3 plus row 1 is the new row 1. Okay? So that next matrix, we're using row 3, 0, 0, 1, 2. We don't want to change a thing there. And we're just dealing with the top row. What does it become? 1. Second? 0. Yeah, nothing changes there. 0, nothing. I mean, it changes to 0 there. And then finally you get a 1. You're absolutely right. Negative 9 times 2 is negative 18 plus 19 is a 1. Okay, what did you want to happen in the second row?
3.
The 3 become a 0. How do you make that happen? Negative 3 times row 3 plus row 2 is the new row 2. Sorry, that's all written on top of each other. So what does your new row 2 look like? 0, 1, 0, negative 1, right? And guess what? That's exactly what we got before. X equals 1, y is equal to negative 1, z is equal to 2. So, pay your money, take your choice. When you get it in row echelon form, do back substitution. It's usually not too hard.
I guess it depends.
Or some pretty easy steps to reduce row echelon form and read your answer. Okay? Because literally that's what you got. X equal 1, y is equal negative 1, z equal 2. Same answer as long as you don't make any additional errors. There you're perfect.
I guess it'd be easier just to keep on going and just keep it in matrices form. That we don't have to go back to the equation type form. It's about the same.
It's about the same. I think they've actually done calculations on number of operations and stuff, and it's really, really very little. Now, there are some things that we will come to do. You've got to get it in reduced row echelon form.
Is there some that you have to do an equation form?
I can't think of any that you absolutely can't. However, you can't get it totally in reduced row echelon forms. Say totally.
Sometimes it's more difficult than others.
Yeah, when you have an infinite number of solutions, yeah, you're going to have, you won't have all your diagonals being 1. You may have a 1 here, 1 in a bigger matrix, think of that. Or it's like this, 1 here, not a 1 there, but all zeros at the bottom. That would be a dependent set of things. So that is, but as long as you have the 0 above that, you're still in a reduced row echelon form, but you just don't have a leading one in the third row because you got all zeros.
So that would be like where two planes are crossing and there's one like parallel?
No, that would be no solution. This would be,
there's a line.
yeah, there's a line, all three planes cross at the same line, basically. Okay. And there could be some others. Okay. So, we've talked through these pretty well, but let's actually write out, because they do put it, I'll be glad when y'all get your books. Okay. How we do it? 3 minutes, I think I got time. Row echelon form and reduced row echelon form. A matrix in row echelon form, so I'm going to abbreviate this row echelon form. Okay, row echelon form.
So is that the people's names or is that group?
No, I mean, the row echelon means sort of the stair step with ones form. You know, now this is like Gauss elimination. Those row echelon form, Gauss elimination, they almost go hand in hand. But see, you can do a matrix that doesn't represent a system of equations and get it in row echelon forms where you're not eliminating anything because you're not coming up with, so that's why they're not exactly equivalent. So here's row echelon form. Any rows consisting entirely of zeros occur at the bottom of the matrix. Now, even if you did your elementary row operations, you wound up with the second or third row or something like that, all zeros, move it to the bottom. Okay, so that's the first. Any rows consisting entirely of zeros, move to the bottom. Okay, number 2. For each row that does not consist entirely of zeros, for each row that is not consisting entirely of zeros. Okay, those are at the bottom. So any rows that doesn't, the first non-zero entry has to be a 1. Is a 1. And that's called the leading 1. Okay? So every row that's not all zeros, the first non-zero entry has to be a 1, and it's called the leading 1. Okay. And then 3, for any 2 consecutive non-zero rows, Okay? Leading one in the higher row is always farther to the left than the leading one in the lower row. Yeah, exactly what you've been doing. Okay? Now, for reduced row echelon forms, reduced row echelon form. Okay? Each leading one has zeros above and below. Only the leading ones. Okay. I wrote it shorter than what they did. Okay. What's that? Yeah, I know, but we're through basically anyway. All right, we will begin next time on example 4, top of page 16. All right. Y'all are good. I have not had a class in this course before that has caught on to things this quickly. Y'all are good. Okay.
That was the class I had at my first high school. Algebra 3.
Right. Okay. Let me give you homework exercises here. I think you can do 1 through 5, any of the odds 1 through 5. Let me make sure that they have odd answers in the back. Pretty sure they do, yes. Okay. Any of the odds 1 through 5, either 7 or 9. Any of the odds 11 through 17. Any of the odds 19 through 23. Any of the odds 25 through 29. Oh, I'm sorry, 25 through 37. Try to do 39. It's a lot bigger, longer, more involved, but see if you can do that one.
What is the size of it?
And stop there, huh?
What is the size of it?
It's a 5 by 5. Then with augmented it would be a 6 by 5, a 5 by 6.
That's weird. Is that okay? Yeah, that'd be rectangle.
So,
It'd be a diagonal, just not including the
right.
after the equal sign.
The last row, column, yeah. And stop there because then you get a homogeneous system. Okay? And we'll pick up those next time. Good deal, folks. Excellent. This is going to be, I think, a fun class. I think we'll get further in this than I've ever got before. Every other time I've taught it, I've had at least one student who is not catching on to those elementary row operations. Oh, I have to go through literally, and so this should be fun.
It's exciting. I know.
I know. Yeah, don't worry. It will stiffen a little bit, but not bad. To me, linear algebra is almost fun.
We were ranking things on easy to hard, and it was linear algebra, top 3 in different.
That's right, definitely.
That's probably about the difficulty.
I think just about